Awesome. Okay. So good morning, everybody. What I'm going to do today is talk about the final section in chapter 3, which is 3.7. So let me write that down here. Which is called limiting reactants. Okay. All right, so let's come over here. There we go. All right, so let's talk about limiting reactants. The way that we'll start is by taking a look at, here we go, the first problem in the set for that chapter, for that section. Okay, so the first problem is called solving moles to moles limiting reactant problems. And in this first question, it says solid aluminum, which is Al, and chlorine. Remember, chlorine is one of the 7 diatomic elements. So Cl2 is written here. React to form solid aluminum chloride, AlCl3. Suppose that you have 11.0 moles of aluminum and 7.0 moles of chlorine in a reactor. Suppose as much as possible of the aluminum reacts, how much will be left? So it's giving you a hint there. There's going to probably be some aluminum left over, and then they want you to round your answer to the nearest 1/10 of a mole, 0.1 moles. Okay, so let's take a look at this one. Okay, so we have solid aluminum. And it's reacting with gaseous chlorine. And it's forming aluminum chloride, which is AlCl3. Okay, so the first thing we're going to do before we do any calculations is write the equation so that we can do calculations. So the reaction is solid aluminum, so Al, and that's a solid, plus chlorine, and that's a gas, and it's going to form solid aluminum chloride. Okay, so when we have calculations to do with a chemical reaction, it's generally a good idea to balance the equation, because the balanced equation is going to give you the relationships between reactants and products so that you can do those calculations. So let's take a look at this one. It looks like there's 1 aluminum on both sides, but there's 2 chlorines on the left and 3 on the right. So there's a couple different ways you could do this. One would be to say, you know, if you got 2 and 3, what's the lowest multiple of 2 and 3? That would be 6, right? So if you had 6 chlorines on both sides, that would be balanced. So how do you get 6? Well, 3 times 2 is 6. And 2 times 3 is 6, right? Remember, you multiply this number times the subscript. So you got 6 chlorines on both sides, but by putting the 2 over here, you now have 2 aluminums. That's easy to deal with. You just put a 2 over here. Okay. Another way to do it, if you're comfortable with the fractions, would be to say that, you know, we have 2 chlorines over here. That's a smaller number. 3 is a larger number. So what would we have to multiply this over here on the right side by to get 2. We want to have 2 over here. So, or we could say, what do we have to multiply this by on the left to get up to 3? So we could try that too. So some number times 2 has got to equal 3. Well, n would be 3/2. So if you put a 3/2 in there, that would give you 3 chlorines on the left. You've got 3 chlorines on the right, 1 aluminum on both sides. So technically that's balanced. That's a balanced equation. It may not look in the form that you typically see it. Actually, that is not an uncommon form of this equation. But if you wanted to get rid of the fractions, you could just multiply everything by 2. And then you just get what we got before. So there's more than one way to balance an equation. However you balance it is fine. Okay, we have the same one right here. Okay, now that balancing act, that gets us to the point where we can do the calculations. So if we come over, and I'm going to write these numbers down, what we're given is that we have 11.0 moles of aluminum, and we have 7.0 moles of chlorine. Okay, that's what's put into the reaction mixture. Okay, so here's what I'm going to do. I'm going to go through this. You'll recognize a limiting reactant problem by the following. If they give you the amount of both reactants or more than one reactant, that's you can use to identify as a limiting reactant problem. If you go back to section 3.6, all of those problems would say something like 11 moles of aluminum with excess chlorine, or 11 moles of aluminum and chlorine is in sufficient quantity to react with it, right? Here they're saying, no, 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 we're going to give you the amount of each one. So you're going to have to take both of those numbers into consideration. Okay, so here's one approach to the limiting reactant problem. What you do is you figure out how much of each reactant can form product. So how much reactant do we have in order to form a product? So what I'm going to do is I'm going to say that we have 11 moles, 11.0 moles of aluminum. Okay. And I'm going to calculate how much product I can get out of that. So let me show you how we do that. Use the coefficients. It's 2 moles of aluminum chloride for every 2 moles of aluminum. Okay, that's what we did last week, last Thursday. Okay, you may not have looked at those videos yet because it was a holiday. 11 times 2 over 2 is 11, so 11.0 moles of aluminum chloride. Okay, so what that does is it allows us to figure out how much aluminum chloride could be made from the aluminum, the solid aluminum. And the reason I say could be is because we don't know whether, at least not yet, we don't know whether that's the actual amount that would be made because we haven't taken the other reactant into consideration. So what I'm going to do now is I'm going to do exactly the same calculation, figuring out how much aluminum chloride we could make, but using the chlorine gas. So chlorine is 7 moles. And we're going to multiply that again, coefficients 2 and 3, times 2 moles of aluminum chloride over 3 moles of chlorine. Okay, so your moles of chlorine are gone. So you get 2/3 of 7, right? 2/3 of 7. Let me grab my little calculator here. That's 14/3. So you get 4.7 moles of aluminum chloride could be produced from the chlorine. So notice you don't get the same number. There's 11 here, and there's 4.7 here. Those are different numbers. So how do we deal with that contradiction? They're contradicting each other, right? One is saying you can make 11, the other one's saying 4.7. So here's the sort of conceptual idea. Imagine I said, I have three pizzas. Okay, actually, let me make them round. So there. So here's your 3 pizza. And I want to make a pizza that has 4 pieces of, I don't know, whatever you want it to be, mushrooms, pepperoni, 4 pieces on it, right? So that's what's required, 4 pieces of that. And I said, okay, I've got these 3 pizzas here with everything except the pepperoni or the mushroom. And now what I'm going to do is I'm going to open up the package of the topping. And there's 8 slices in it. And I'm going to ask, how many completed pizzas could we make? Well, we know we need 4 of these for every pizza, right? So those 4 could go over there. And we have 4 over here, so we can put them over there too. And boy, this one doesn't have any, right? So that one can't be completed. So that one's going to be unused. We can't sell a pizza without these toppings. So that means we could only make 2, right? The answer would be 2, even though we had the bread for 3. So that's essentially the limiting reactant problem. That's what we're doing in chemistry. We're saying, look, we have enough aluminum to make 11 moles of aluminum chloride, but we only have enough chlorine to make 4.7 moles of aluminum chloride. So the answer would be the smaller number, 4.7. So the answer is, in the end, we can make 4.7 moles of aluminum chloride, just as we could only make 2 pizzas here. And the way we're calculating that is by taking the amount of the reactant and then multiplying it by the relationship between the substance we're interested in and the substance that we're starting off with. You do it for both, and then just pick the smaller number, right? So if I had put in 21 moles of chlorine, you get a different answer, because 21 times 2/3 is 14. So you get 14 moles. So now suddenly the aluminum would be a smaller number. And so aluminum would then give us the answer, 11 moles. Okay. So coming back to the question, that's not really what they're asking. What they're asking is there any aluminum left over? And that's a little bit more of a complicated problem. This is actually a little tricky here, because the first question they ask is conceptually involved. It's not a very simple answer. What I've shown you here is how to use the amounts of the reactants to find the amounts of the products. But now we want to know how much of one of the reactants is left over. Okay, so let me make a little space here. I'll get rid of the pizzas. And actually, we don't need to have all that wording. There we go. Okay, so we have our answer here in terms of how much aluminum chloride could be made. But now the question is, how much aluminum is left over? Well, with the pizza problem, the answer is very simple. 1 pizza, right? We had 1 incomplete pizza, so that's left over. We didn't have the toppings for it. Okay, that's very simple. But here, it's a little bit more involved. So here's how we could go about it. What we know is that 7 moles of chlorine gives you the 4.7 moles of aluminum chloride. So that's how much chlorine was used. So if that's how much chlorine was used, how much aluminum would have been used. So the first step is how much aluminum would be used if 7 moles of chlorine was used. Okay, so now we're looking at the relationship between these two. The relationship is 2 to 3. You'll hear that terminology when you watch videos and read books and stuff. The ratio is 2 aluminums get used for 3 chlorines. So we know that all the chlorine got used. So 7 moles of chlorine was used. And the relationship is every time 3 chlorines get used, 2 aluminums get used. So I'm going to write that as 2 moles of aluminum used for every 3 moles of chlorine used. You don't have to write used in here. I'm just doing that just so you can kind of see what I'm talking about. So if you take 7 times 2/3, what you get is 4.7 moles. Okay, so I'm going to cancel those, and what you're left with is moles of aluminum used. Now, again, that's not the answer. That's not what they were asking. The question was, how much aluminum is left over? How much is unreacted? How much was not used in the reaction? So how do you figure that out? Well, step 2, the amount unused is equal to the starting amount minus the amount used. Okay, so think about it. In the pizza problem, we started with 3 pies. We used 2 of them. So to figure out how much is left over, you take what you started with, 3, you subtract what got used, 2, that leaves you with 1, right? 1 unused pie. Same thing here. You take what you started with for the aluminum, 11 moles. You subtract off what got used. Okay. Wait a minute. Yeah, okay. 7, okay, so, right. 4.7. And then that's going to give you 6.3. And I'm running out of room here, but it says remaining 6.3 moles. Okay. All right. So this equation here, the balanced equation, can be used to figure out many different things now. We've expanded how that equation can be used. It can be used to figure out if a certain amount of this is reacted, how much of this is going to react. It can be used to figure out if this amount is reacted here, how much of this is produced. We can also figure out now how much of the what's called the excess reactant remains after the reaction by doing these calculations. Okay, so let me show you another example. I'm going to stop that one and we'll just bring up another example here. Oops, don't do that. There we go. Oop, that looks like it's the same reaction, I think. Or no, that's actually was a different reaction. Okay, here, let's try this one. So this one's interesting because it looks like there's 2 reactants and 2 products. So it's a little bit more complicated equation. So that means we have to balance it. So ammonia, which is NH3, is a gas at room temperature. Oxygen is a gas at room temperature. They react to form nitrogen gas and water vapor. So it looks like everything in this equation is a gas. A vapor is a gas. Suppose you have 1 mole of ammonia and 7 moles of oxygen. Calculate the largest amount of N2 that could be produced. The largest amount of N2 that could be produced. Okay, so let's take a look at this one. So it's ammonia plus oxygen to form nitrogen and water. Interesting reaction. So ammonia and oxygen form nitrogen and water. Okay, so again, before you do any calculations with an equation, make sure you balance it. Okay, so what are we going to start off with? Well, let's see. It looks like we have 2 nitrogens on the right side and only 1 on the left. So I guess we could put a 2 here. So that'll give us 2 nitrogens. By doing that, you also now have 6 hydrogens on the left, right? 2 times 3 is 6 hydrogens. So if you put a 3 times 2 is 6, you now have 6 hydrogens. So now the only issue is the oxygen. The oxygen is not balanced. So what I'm going to do is I'm going to say, look, you got 2 oxygens over here, and you got 3 over there, right? 3 oxygens on the right. So I'm just going to put a little n here. So 2 times n has got to equal 3. So if you divide both sides by 2, you get 3 halves. Okay, so now you've got 3 oxygens on both sides, so that's balanced. Everything's balanced there. If you want to have the whole numbers and not have any fractions, then you can just multiply everything by 2. So if you multiply the entire equation by 2, you get rid of the half. Okay, so now we have a balanced equation. Let's get rid of this. And now we can do the calculations. Okay. So the calculations, here's the numbers, and we have to be careful. You have to read these very careful. They're going to ask you a specific question, and it's not always the same question. So suppose you have, so this is what's given. You have 1 mole of ammonia. And you have 7 moles of oxygen. And then in it, they say calculate. So you're going to calculate the largest amount of nitrogen that can be produced. Okay. So let me show you again an analogy. So before we do this actual calculation, I want to show you an analogy. And again, what we could do is we could say, look, you've got some number of pizza doughs, right? So suppose I said I've got all these pizza doughs. And then I'm going to have these little toppings. These ones are little squares. Okay. And then I'm going to tell you that the formula for a completed pizza is 3 toppings. Okay. Now, here's what you can do. We can write this as a dough. So you need 1 dough, right? The completed pizza has 1 dough. So it's D. And then you need 3 toppings. So it's 3T, 3 toppings. That's going to give you a completed pizza, which we could write as DT3, right? DT3 is 1 pizza and it has 3 of the toppings for every dough. All right, so there's your balanced equation. So now what I can do is I can say, okay, well, how many doughs do I have? 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 doughs. That's how many I'm given. And I can get 1 completed pizza. So 1 completed pizza for every dough. So that means I have enough dough to get 8 completed pizzas, right? But we also have to consider the other reactant. The other reactant is we need 3 toppings for every pizza. So how many toppings do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we also have 12 toppings, and it's 1 pizza for every 3, right? 1 for every 3 toppings. So that means you can get 12 over 3, which is 4 pizzas. So the answer then would be not 8. We don't have enough toppings to make 8 pizzas. We have enough toppings to make 4 pizzas. So the amount of pizza that we would make would be 4. Okay? We're doing essentially the same thing with these 2 reactants. Here's our balanced equation. And in this particular question, they're asking us for the nitrogen. What's the maximum or the largest amount of nitrogen that could be formed? Just like the largest number of pizzas. What's the largest number of pizzas we could make? Okay, so let's erase the pizzas. And we'll work on the nitrogen. Okay, so the way that I did it with the pizza was I started with the doughs, and then I did the toppings. So we'll do the same thing. We take what we're given in terms of ammonia, 1 mole of ammonia. Now remember, a mole is a very big number, 6 times 10 to the 23rd. So we're not talking about 1 pizza, we're talking about 6 times 10 to the 23rd pizzas, but in any case, it's the same, conceptually the same. And we're interested in nitrogen, so it's 2 moles of nitrogen for every 4 moles. I'm using this balanced equation here, 4 moles of ammonia. So it looks like we have enough ammonia to give us a half a mole, 0.5 moles of nitrogen, okay? So I have a sneaking suspicion that that's going to be the answer because it's a pretty small number. Now, if you take the other reactant, 7 moles of oxygen, okay, and 7 moles of oxygen times 2 over here, it's 2/3, right? 2 moles of N2 over 3 moles of O2. Well, that's the same number we were getting in the previous problem. I think it comes out to 4.67 or 4.7. 4.7 moles of N2. Okay, so see how it's 4.7? This is much larger, right? So you might think, oh, that's the maximum amount we could make, but that's not true. Just like the pizza, even though we had 3, all those doughs, 8 doughs, we couldn't make 8 pizzas because we didn't have enough toppings to make 8 pizzas. Same thing here. Even though we have enough oxygen to make 4.7 moles of nitrogen, we only have enough ammonia to make half a mole of nitrogen. Okay, so you pick the smaller number. So this would be our answer here. This would be the maximum amount of N2. Okay, let me just make sure. Okay, that's good. All right, and so you pick the smaller of the 2, and there you go. Okay. So that's 2 types of problems, but both of those types of problems are in the same kind of question. That's that first question from section 3.7. So the first one was, what's the maximum amount of something that can be made? And then the second one was, how much is going to be left over of the one of the reactants. So a little bit of terminology. The reactant that produces the smaller amount of product in your calculations. Okay, so in that case, that would have been the ammonia, right? The ammonia gave us a smaller amount of nitrogen. We call that the limiting reactant. Okay, it's called the limiting reactant, the reactant that gives you the smaller number in your calculations. The reactant that produces the larger amount of product in your calculations is called the excess reactant. Okay, so for this particular problem, the limiting reactant would be the ammonia, and the excess reactant would be the oxygen. Okay, the amount of product from the calculations. Okay, so we just did the amount of product from these calculations. The smaller amount, right, is called the theoretical yield. Theoretical yield. Yield is spelled Y-I-E-L-D. In chemistry, yield means how much did you make? Okay, so if you could use it in financial terms too. So like if you were, let's say you're waiting tables. At the end of your shift, you say, okay, how much did I make in tips? That would be your yield, the total amount that you got at the end. So in this particular problem, the maximum amount of nitrogen that got produced was the smaller number. It should be the smaller number, which is 0.5 moles. So for this one, the theoretical yield would be 0.5 moles. It turns out the larger number, in this case 4.7 moles, is not a very useful number. It actually doesn't give us any information or very little information that we can use. The useful piece of information is the smaller amount, because that's what will happen in reality, and that's called the theoretical yield. Okay. Let me see here. We got a little. It's like students having a problem. Hold on. Students having a little problem here. Me. There we go. Okay, hopefully they can get on. They may have tried to get on and oh, here we go. Good, awesome. There we go. Great. Okay, so that's the first type of problem in terms of limiting reactants, where they're giving you the amount of moles. But as you go back and you look at section 3.6, what you'll find is that for many of these problems, grams are what's going to be used. So in the laboratory, we generally weigh things out, right? And so weights are in grams, and generally we don't have a device that can measure moles. It'd be kind of cool if we had a machine that could measure out the number of moles of the substance by counting them. But so far we don't really have that kind of technology. Maybe one day. For right now, what we have are devices that can weigh things, balances and scales. So most of the problems that we do involve that. So let's take a look at another calculation here. Here we go. All right, and let's share the screen. There we go. Okay. So in this particular problem, it's called limiting reactants. It says here that aqueous hydrochloric acid. So in the next chapter, we're almost there. When we get to chapter 4, we're going to start talking about aqueous reactions. So acids and bases, precipitation, reduction oxidation reactions. Gets interesting. Aqueous hydrochloric acid, by the way, hydrochloric acid is the acid that's very, it's the main acidic constituent of gastric juice, of the first step, one of the early steps of digestion. HCl is what's called a strong acid. So hydrochloric acid reacts with solid sodium hydroxide, which is sometimes called lye, Lye, to produce aqueous sodium chloride, that's table salt, right? And liquid water, H2O. Suppose 21 grams of hydrochloric acid is mixed with 10.2 grams of sodium hydroxide. Calculate the maximum mass of water that could be produced by the chemical reaction, and then round your answer to 3 significant digits. So in a sense, this is kind of like the problem we just did. You've got 2 reactants, 2 products. They're giving you the amount of the first reactant, they're giving you the amount of the second reactant, and they're asking you for how much product you're going to get, one of the products, right? In this case, water. The difference here is they're not giving you the number of moles. When they give you the number of moles, all you got to do is use the balanced equation, multiply by the ratio, do it for both, pick the smaller number. Here, we have to do a conversion from grams to moles because the balanced equation doesn't give you a relationship between masses. It gives you a relationship between moles. It's essentially ratios, right? So like if I said, hey, we've got H2O. H2O has 2 hydrogens, 1 oxygen. That doesn't mean it's 2 grams of hydrogen and 1 gram of oxygen, right? The weights are different. What it means is there's 2 moles of hydrogen for every 1 mole of oxygen. That's what the formula gives you. And that's what a balanced equation gives you. So if we're given grams or kilograms or milligrams or micrograms, we first have to convert them to moles and then go through the calculation. Typically, the problems will be stated in such a way that once you've got the number of moles of product, you figured it out, then you got to convert it back to grams. So it's this mass to mole conversion, and then in the end, mole to mass conversion. So that comes up over and over in chemistry. Remember what we said last week was, if you have the mass and you want to find the moles, you divide by the molar mass of the compound. If you have the moles of the substance and you want to find the mass, you multiply by the molar mass, right? So it's like a conversion factor. So that comes up over and over again. So we're going to take a look at this one. This one is an acid-base reaction. This will be a very familiar reaction to you by the end of the next chapter. Hydrochloric acid, sodium hydroxide, that's a classic acid-base reaction. And acid-base reactions very often produce a salt plus water. And that's exactly what's happening here. Okay, so let's stop share there. And let's start it here. Okay, so actually the balanced equation is pretty simple because hydrochloric acid, HCl, if it's dissolved in water, we use the term aqueous. So AQ for aqueous. And it's reacting with sodium hydroxide, NaOH, aqueous. And then it tells you that it forms sodium chloride. It gives you the formula and everything. It tells you it's aqueous. And then liquid water. So it kind of gives you everything. The nice thing about this particular reaction, again, it's a classic reaction. Many laboratories, you would do this in the first semester of chemistry. We do it in the second semester in our sequence. That particular reaction is already balanced. You don't even have to change the coefficients to figure out how much of the products you're going to get. There's 2 hydrogens on the left. One is in the HCl, one is in the sodium hydroxide. And then there's 2 hydrogens on the right side in the water. There's 1 chlorine in the HCl and 1 chlorine in the sodium chloride. And there's one sodium on both sides and there's one oxygen. So it's already balanced. That's the kind of nice thing about this one. Some acid-base reactions are a little more complicated, but this one is pretty simple. However, what they do tell you is that 21 decimal grams, so right, in ALEKS, they insist that you put the decimal right after your number, and it's mixed with 10.2 grams. So notice what I'm doing here. Notice this is for, I don't know if this is the first time.
Wasn't it 2.1?
Oh, let me check. Actually, it's 21.
Oh,
It's 21. Yeah, I'm looking at it right now. It's 20. You would think it, well, actually 21 makes sense. 2.1 would also make sense. Yeah. Well, I'm not going to stop the share on the screen here because it'll lose all the work there. Okay. Yeah. So it's 21 grams. Okay. So notice I wrote the masses right underneath the reactants. That's a very common technique when you're problem solving. So in physics, you do this a lot. You draw a little picture of what's happening and then you put your numbers under where it's happening. So like you draw a little box and you write the mass inside it, that kind of thing. We do that a little bit in chemistry too. So in the balanced equation, we write the amounts right underneath the equation. Okay. So that way you can kind of see what's going on a little bit. Okay. So the question was, let me come back here. What was the amount of water? So what is the mass of the water that is going to be produced in this reaction? Okay. And taking it back to the previous section, which is 3.6, I think I showed you a little flow chart where I said, look, it's very often the case where they give you the mass of the reactant. In this case, let's say HCl. And what you do is you divide by the molar mass to give you the moles of that substance. Okay, so it's the same flow chart. Then what you do is you use the balanced equation to find the moles of the product that they're asking about. So in this case, it's the water. Okay, so you use the balanced equation. So I'm explicitly writing in the coefficients, right? If there's no number, it's a 1. So it's, you multiply by 1 mole of H2O for every 1 mole of HCl, right? So you're using the balanced equation. And then typically they're not going to want to know the number of moles of the product. They're going to want to know the number of grams, the mass. So what you do is you multiply by the molar mass. In this case, it's water. In this case, you're dividing by HCl, right? And that's going to give you the mass of water. Okay, that's what we did in section 6. The difference here is that they now give you a second reactant, and you have to take that into account. So here's what will work. This is one method. This is the method I use. What I do is then I just do exactly the same calculation with the second reactant, with the sodium hydroxide. So I take the mass of sodium hydroxide and divide it by the molar mass. Okay, and that's going to give me the moles of sodium hydroxide. Then I multiply it by the relationship between the substance we want. So 1 mole of H2O divided by the substance we're given. And that will give us the moles of the product. We want the product in this case. And then multiply by the molar mass of the product. And that will give you the mass of the product. Now, what's different about this problem is that this flowchart, of course, has 2 steps, right? 2 chains. Now, because it's a limiting reactant problem, you just pick the smaller number. So you choose the smaller number or the smaller value. Okay, and remember, the smaller value is called the theoretical yield. The reason we use the term theoretical is because you're calculating it. You're not in the laboratory measuring it, you're calculating it from the balanced equation. So a chemist, what they'll do is they'll say, hey, I want to make this amount of a product. How much of the reactant do I want to put in? How much of the other reactant do I want to put in? And then they essentially know what the theoretical yield is, how much you're going to get. So they put in the amount of reactants to give them that. We typically don't give as many problems like that in General Chemistry 1, but if you were to take another more advanced course, you would do that more often. That's the more common thing you would do. Okay, which is, makes more sense. So there you go. There's your two flowcharts. So now what I'm going to do is I'm just going to go ahead and go through these calculations. We'll pick the smaller one. And so let's start with the HCl. 21 grams of HCl. The molar mass of HCl, you got to get fast and good at this, right? The molar mass, hydrogen's 1.01, chlorine is 35.45. So if you add those together, you get 36.46. So you divide by it, right? So 1 mole of HCl divided by 36.46 grams, right? That's the molar mass in the denominator there. Dimensional analysis shows you that by dividing by the molar mass, that will give you the moles of HCl. So 21 over 36.46, and you get 0.57597 grams of HCl. So there's our first step. Our second step is we use the balanced equation. We want to find out how much water we're producing, right? So it's 1 mole of water for every mole of HCl. So even though it's 1 divided by 1, we all recognize that 1 divided by 1 is 1. So if you're multiplying by 1, that's not going to change the number. I'm still going to write the step here, because if it's not a 1, if there's any number that's not 1, if the numbers are different, then you're going to get a different value. So HCl now cancels, and you get 0.57597 moles of water now, right? So we're making it. We're trying to get the water. We're getting closer. We've got the moles of water. Now we just want to figure out how much it weighs. Really, all you're doing is you're saying, here's how much the HCl weighs. How many is that? Once you've got the number of them, then you can say, okay, if I have this number of HCl, how many numbers of water is that? Once you've got the number of water, now you just want to figure out how much it weighs. So the third step is just to multiply by the molar mass right here. So 0.57597 moles of water times water is 18.02. That's the molar mass of water. Okay, so you take that number times 18.02. How did I get 18.02? Let me write the number down here first. Okay. Now, in a sense, you have a 50% chance of being right if you stopped right there, because it's possible the HCl was the limiting reactant. And if it is the limiting reactant, that would be the answer. But we don't know that for sure until we do the second set of calculations. I'm going to ignore the significant digits for right now. We'll come back to it at the end. So now we do the same thing with the second reactant. Mass of sodium hydroxide, divide by the molar mass to get the moles. Use the balanced equation to get the moles of the product. Multiply by the molar mass to get the mass of the product. Then we choose the smaller number. Okay. So our second set of calculations is 10.2. grams of sodium hydroxide. Now, sodium hydroxide is an interesting compound in terms of its molar mass, because sodium is 22.99 and hydrogen is 1.01. So the 0.99 is a little under and the 0.01 is a little above. So they average out. So 23 plus 1, 24. And then you add the oxygen, which is 16.00, and that gives you 40.00. It's a really nice molar mass for calculations, it's 40.00. That doesn't happen too often with compounds. Usually they're point something something, but sodium hydroxide is 40.00. And that actually, you can do the arithmetic pretty easily. So times 1 mole of sodium hydroxide over 40.00 grams of sodium hydroxide. Of course, if you're using the periodic table that has extra digits, so 1.00794, then it's not so nice of a number. Then it's like 40.0018 or something like that. Okay. So that's going to give you 10.2 over 40 is 0.255. Okay. And then the relationship between sodium hydroxide, I wrote it here as step 2. It's 1 to 1, right? Everything in here is 1. So 1 water for every sodium hydroxide. So 0.255 moles of sodium hydroxide. And it's 1 mole of water over 1 mole of sodium hydroxide. Again, if those coefficients are not the same, then you're going to have that, a different number. The moles of sodium hydroxide will be different than the moles of water. I'm sorry, this is water. All right, we're figuring out how much water we have now. So we're almost there. Once you've got the moles of something, just multiply by the molar mass to get the grams. So step 3 times the molar mass of water. So 0.255 times 18.02 you multiply by the molar mass. Why is it 18.02? Each hydrogen is 1.01, so that's 2.02, and then oxygen is 16.00, so 2.02 plus 16.00 is 18.02. And you get 4.595 grams of water. So now we have 2 answers. Remember, we picked the smaller. So the smaller one's right here. So that's going to be the answer. So this is not useful. We don't even use that number. Sometimes this happens in physics if you're doing trajectories, like something's falling up and down. You solve for the problem and you get 2 answers. You pick one, the other one's not really all that useful. Same thing here, that 10.39779 is not that useful. The smaller is the useful. So our answer's right here. So we call this the theoretical yield. I haven't rounded it yet. Okay. Remember, the reactant that gives you the smaller amount is called the limiting reactant. Okay. So that means it looks like the sodium hydroxide is the one that gave us the smaller amount. So this is the limiting reactant. The reactant that gives you more of the product is the excess reactant. So that would be the HCl. Okay, this is called a product. So is this. This is called a product. And the theoretical yield, I'm going to round it now. It looks like we had 2 significant figures there. But that actually didn't get used in our final answer, right? The 21 wasn't used over here. It was used over here, but not here. The 10.2 was used over here. It's right there. So that's 3 significant digits. So our answer should be rounded to 3 significant digits. So 4.59, I guess you would round that up to 4.60. 4.60 grams of water produced. So 4.60, that's the theoretical yield. Okay. Now there is a way to cut a step out of this. You can cut a step out by doing the following. You can make it a little comparison. In both calculations, both set of calculations, the last step was to multiply by 18.02. So since you're doing the same thing in that last step, what you can do is you can say, look, for the HCl, we got 0.57 moles of water. And for the sodium hydroxide, we got 0.25 moles of water. This number here is smaller than this one is. So there's no point in doing this final step here because since this is smaller here in moles, since this is larger in moles than the 0.255 is, the grams is going to be larger too. So we don't need to do that last step for grams, but that only saves you a few seconds in that calculation. And in the end, you don't know which one it is anyways. So there you go. Okay, so if you want to leave that step out, you can, but I would recommend doing it because it doesn't really save you that much time. Okay.
Quick question.
Yeah.
On the exam, when we're giving our answers, is there going to be kind of like a tolerance and deviation with our rounding? Like I ended up getting like 4.61. Just if we're like rounding differently someplace, is that going to be okay, or is that going to be like marked wrong?
It will mark it wrong.
It will mark it wrong.
And typically what I do is after everybody has submitted their exam, I go back and look at them. And if I see, so for example, if you put 4.61 and they said it was 4.60, I go back and give, 90 to 95% credit for that particular question. Okay. So in the end, it will give you a 0, which can be frustrating. You're like, wait a minute, I was only off by 1%. It'll give you a 0, but I will go back and regrade it. And I will give you 90 to, depending on, how the error is. So for example, if you put, 4.7 and it was 4.6, I might take off 10% for that. If it was, you put 4.61 and it wanted 4.60, I want to take off 5% for that. So
yeah,
it will be part of your grade, but
I ended up rounding the 0.255 to just to 0.256 because it was like 0.255555, so I just rounded that. And then the periodic table that I'm using, it pretty much like gives hydrogen as 1 gram per mole. It's like 1.008, so I just used 1 instead of 1.01. So that's just accounting for the just slight discrepancy in the decimal.
Yeah, I would recommend when you take the exam to use the periodic table that Alex provides.
Okay.
Okay. And the reason for that is that the programmer is kind of interesting. The way the programmers have set it up is they pick numbers that are, you get a lot of numbers of like 0.49 or 0.51. And if you're at 0.49, you would round one way. And if you get 0.51, you would round another way. So it ends up that the way they pick the numbers, it becomes very sensitive to how many significant digits you're using in your periodic table. So if you use the value that's in Alex and then go through the significant digits, it will give you the same result they get, as opposed to if you use a different periodic table, which has a different number of significant digits. Even if you follow all the rules right, you'll get a slightly different answer.
Yeah. Okay.
So that would be my recommendation.
Okay.
So if you take the exam and you get 4.6 and it said no, it's 4.61 and you get a 0 for that question, don't stress over it yet. I'm going to go back and look at it. It may take me a couple days, but I'll go through and look at it, and then I can add in some credit for that. Okay. Good question. All right, let's see. So let me take a look here and see if there's enough time here. Okay, not enough time to go through that. So I'll tell you what, so tomorrow what we'll do is we'll start with the theoretical yield calculation. That's the last one for this section and the last one for the chapter. I was going to start chapter 4 tomorrow, but I want to provide enough time to really go through this theoretical yield of chemical reactions. We've kind of gotten into it a little bit here, but we're going to go over it. We'll start with that. So that'll be the end of chapter 3, and then we'll start on chapter 4 tomorrow. Okay. Let's see. Yeah. So we'll finish up 3. We'll start on chapter 4. And there we go. Okay. Very good. Thanks for being here today. And
I have a
there any
question about the lab.
yeah, go right ahead.
I'm still not being let on campus, and you said last week that you would post a lab
Yes.
videos.
Right.
Yeah.
So for those of you that are in the section B where you're doing the labs on campus and you're not getting on campus, what I have to do is I have to upload some stuff to Blackboard to your lab section that I haven't gotten around to doing yet, but I'm going to do that today. I will upload those to you. Look for those later in the afternoon, maybe early evening. It should be be careful, it'll be in your Blackboard lab section, which for you would be LB, right? So not the regular, lecture Blackboard, but in the LB, and the documents when I upload them will be in the course content. Okay. So, some of you that's last week and this week. So I will get, both weeks uploaded today. And
Okay, thank you, Professor.
Start working on that. Absolutely. Okay. Very good. All righty. So have a great day. Reach out to me if you have any questions. And in terms of office hours, I do give office hours if you're interested. So we can always do a Zoom meeting at some point. We'll just arrange it for a time that works for both of us. And have a great day.
First, I have a question.
Mm-hmm. Go ahead.
It's about the specific Alice question. It's like the using the Avogadro's number. So I'm having an issue like knowing when to use scientific method, like the scientific function of the
Notation.
calculator.
Yeah.
So it keeps on, and so it keeps on giving me the answer as wrong because it's not like in the scientific notation, but I'm not quite sure when to use the scientific function in the calculator.
Usually scientific notation is used when the numbers are either very large or very small. So for example, if you're doing a calculation where it's 3.6 divided by 18.02, usually you don't have to use scientific notation for that. So the questions we just did a little bit earlier, like all those limiting reactant problems, never did I use scientific notation for those. But when you're dealing with calculations with Avogadro's number, then you're going to have to use scientific notation because Avogadro's number is so big, right? So when we do like later in the course, when we start doing like the sizes of atoms and the number of electrons and stuff like that, we'll be using scientific notation quite a bit. Depending on what calculator you have, it's usually a relatively easy thing, So the idea would be you just enter in the decimal, like 6.022. And then most calculators have a button, which is capital E, capital E. There's 2 capital E's. So you hit that, and then you enter in the exponent, 23, for example. And then if you look at the display, it'll say 6.00, and then it'll have a little 23 above it, right? And that means times 10 to the 23. So if you're having problems knowing when to use scientific notation or how to use it, probably the best thing to do is to just, let's find a time where we can talk about it. So if you want to do it like after this meeting right now, you could just stay on. I'll stay on for a few minutes if you want to do it now.
Okay.
Or what you could do is you could find the problem that you're having a difficulty with and then reach out to me and then we could go over it.
Okay, I have tutoring for computers now, but we can schedule a time because I was struggling before.
So I'm sure you have this, but you can always, just text me at this number, right? And we'll arrange a time so that we can go over it. Do you have tutoring for chemistry?
No, I didn't sign up for it yet.
Okay. I would recommend doing that too, you know. So there's two options in terms of tutoring. There's one through the library, right? So the library provides tutoring. But also the college has a relationship with tutor.com now. And so, there's a couple different sources there. So, that's another way to do it. But you can also reach out to me and we'll find a time and we could go over it. So, it's a little harder to do. Are you, Bianca, I can't remember, are you on campus? Are you doing the lab on campus or are you the off campus?
No, I'm off campus.
You're off campus. Okay, so you're not gonna be on the campus. All right. So just reach out to me and then, we can go over it. I'll just open up a Zoom and you can pull out your calculator and go through it.
Okay, thank you.
All right. Take care.
Thank you, sir. Bye.
Bye-bye.